Hello friends, welcome to the Arpit course on numerical methods in civil engineering. I am Yogesh Desai from Department of Civil Engineering, IIT Bombay. This course is being offered in a modular form consisting of 5 modules, and today we will discuss lecture 1 of module 3 related to classification of differential equations. Earlier we talked about mathematical description of a given physical problem. On the basis of our understanding of problem, we express this physical problem in terms of an equation which could be algebraic or integral or differential equation. So, now we are discussing characteristics of differential equations. They are also referred to as rate equations, and typically differential equation is composed of an unknown function and its derivatives. Classification of differential equations is very important in any numerical work. Depending upon the classification of differential equation, we come to know how many supplementary conditions are required to solve the given differential equation completely and uniquely. Also, which kind of method to be used also depends on the characteristic of the differential equation that is given to us. So, in this context, study of classification of differential equations plays very important role. So, most of the things you would have studied earlier. So, just we will provide an overview on classification of different differential equations. So, we start with ordinary differential equations, and for convenience we show them in a very compact form. X here is independent parameter. Once we talk about ordinary differential equation, basically it is the differential equation in one independent parameter space, and for example, that parameter space is x. So, we have not only the function, but also one or more of its derivatives as we have shown here. So, u is the dependent variable and x is the only independent parameter. Solution of differential equation, unlike algebraic equation, it is a function here. So, if we talk about first order differential equation dx by dt equal to x, obviously we infer from here that x is a function of independent parameter t, and if I want to determine whether k times e raised to t is a solution to the given differential equation, we substitute this expression in the given differential equation, and if it satisfies the given differential equation for all values of t, then we say the expression thus used is a solution of the given ordinary differential equation. Similarly, we can talk about partial differential equations. One such equation is given in a compact form as shown here. Equation A, x, y, z etc. are independent parameters. U is the unknown function continuously varying with respect to x, y, z, and ux, uy, uxx etc. are its partial derivative. So, in the sequel, when I say u subscript x, that is partial derivative of u with respect to x. When I talk about u subscripts y, that means we are talking about second order partial differentiation of u with respect to y. So, subscript tells us with respect to which independent parameter we are taking the differentiation. Partial differential equation contains partial derivatives of the given function u with respect to independent parameters like x, y, z. If u satisfies the given equation A identically at each and every point, it is referred to as solution of A. Now, given differential equation may not have one solution. it may have multiple solutions, and out of these multiple solutions we attempt to select a particular one by introducing additional conditions. One important point to note that the solution may or may not exist, and as I mentioned, may or may not be unique. So, differential equations are very interesting variety of equations to study. Some examples of partial differential equation in two-dimensional space: u x x, that is u del square u by del x square plus del u by del x equal to y, del square u by del x square plus 2 y del square u by del x del y plus 3 x del square u by del y square equal to 4 sin x. And similarly, we can see the other examples: u x square plus u y square equal to 1 and u x x minus u y y equal to 0. Number of partial differential equations we can think of depending upon the physical problem that is being described mathematically. Now, if you consider a function in two independent parameter space x y to be x plus y cube or sin x plus y, we can see that they both satisfy the given partial differential equation del square u by del x square minus del square u by del y square equal to 0. So, that you can check. So, these are possible solutions of the given partial differential equation. Let us talk about various terminology that we commonly use to describe the given differential equation. When we talk about order of the given differential equation, it is the highest power derivative present in the given differential equation. For example, if we see here del cube u by del x cube plus x del square u by del y square plus u equal to 7 y, the highest power derivative is 3. So, this is third order PDE. Why PDE? Because we are given two independent parameters x and y. So, we infer that u is function of two independent parameters and hence partial differential equation. Linear partial differential equation is that equation which is linear in the unknown function and all its derivatives. The coefficients of all the terms depend only on independent parameters. So, that is how we identify whether the given differential equation is linear or not. If you see the example here, y del square u by del x square plus 2 x y del square u by del y square plus u equal to x, this is second order PDE, because the highest order derivative in the equation is 2 and the coefficients of all the derivatives and functions are made up of only independent parameters. So, this is linear PDE. If all the coefficients are constant, we say that we are working with constant coefficient linear PDE. The coefficient remains constant throughout the domain over which the differential equation is described. Quasi-linear PDE. In some classical texts, there is a mention of quasi-linear PDE. On the other hand, in many textbooks, they talk only about linear PDE and non-linear PDE. This additional variety has been introduced because there are certain numerical methods which can be used very efficiently and expeditiously if the nonlinearity is contained in lower order derivative or in the function. That is where this quasi-linear equation comes into play. So, for example, if we see here, we are given second order differential equation del square u by del x del y plus u times del u by del x equal to y. So, if you look at the coefficient of the highest power derivative is 1, whereas the coefficient of lower order derivative del u by del x is u, which is unknown function. So, we say non-linearity is contained in the second term, which does not pertain to the highest order derivative. So, we say the given differential equation is quasi-linear. Okay. Non-linear PDE, a partial differential equation which is neither linear nor quasi-linear is called non-linear PDE. So, it contains non-linearity in its highest order derivative. For example, if I talk about the earlier equation with small change, this multiplier u now is shifted to the first term, u times del square u by del x del y plus del u by del x equal to y. So, now we have non-linearity in the highest order derivative term. That is where we have product. So, either product or powers of highest order derivative, then we say we are working with non-linear differential equation. Okay. Other example, as I was saying, power of highest order derivative, square of del square u by del x square plus del u by del y equal to 0. If this square term would have been applied to del u by del y, it would have been then quasi-linear PDE. So, let us look at some examples, but before that I want to discuss one more thing, and in order to see what that thing is, let me consolidate all the terms dealing exclusively with independent parameters in this function g. G is wholly made up of x, y, z, etcetera, all independent parameters, and then we have the unknown continuous function u and its partial derivatives with respect to independent parameters x, y, z, so on and so forth. If this function g is 0, we say we are working with homogeneous partial differential equation. On the other hand, if this function g made up of all independent parameters is non-zero, it is non-homogeneous partial differential equation. So, let us look at some examples. Del square u by del x square plus x del u by del y equal to y. So, the way we describe the given differential equation is first we look at the order of differential equation. So, what is the order of this differential equation? Highest order derivative. So, that is 2. Then we look at whether it is linear, non-linear or quasi-linear. So, in this case it is linear, and why do I say it is linear? Because the coefficients of the derivatives are independent parameters, and we also have a term in independent parameter space. So, that is what I was talking about, the part of function g. So, that term is present here. It does not contain unknown function, okay, only some function of independent parameters, or it can be a constant term. So, now we say it is non-homogeneous, and obviously we are talking about partial differential equation. So, the way we would term the given differential equation as second order linear non-homogeneous partial differential equation. Let us look at another example. U x minus sin x u y equal to 0. Always look at the highest power derivative first. So, that is second powered. So, this is second order. Is it linear, non-linear, quasi-linear? For that we look at the coefficients of the derivatives and the function. The coefficient of the highest power derivative is made up of independent parameter x, but if I look at the first order derivative del u by del x, it is getting multiplied with the function itself. So, this term is non-linear. So, overall this is quasi-linear equation, homogeneous, because we do not have a function containing exclusively independent parameters. So, the classification of this differential equation is second order quasi-linear, homogeneous partial differential equation. Another case, this is first order, yes, you got it right, non-linear, homogeneous partial differential equation. What about this fellow? Mind you, do not get confused. Log x may give you impression you are dealing with non-linearity. For the given value of x, log x is just a number. For given values of x and y, sin x y is just a number. So, we only look at the derivatives, multiplication of derivatives of the unknown function, power of unknown function, etc., to identify presence of non-linearity in the differential equation. So, this differential equation would be second order, linear, non-homogeneous partial differential equation. I hope you are getting the hang of this. Let us look at one more example. So, tell me what kind of differential equation are we dealing here? Yes, this is third order, quasi-linear, we have log u term, homogeneous partial differential equation. Okay. This one is second order, non-linear, non-homogeneous partial differential equation. Okay, so, I hope you are getting the idea as to how do we describe a given differential equation. So, there will be some more practice for you in the assignment, okay. But this classification is very important. This is the starting point on the basis of which we select appropriate numerical method. Before we proceed, differential equations are very interesting. You solve differential equation once, actually it gives you solution for family of parameters. So, that is the beauty of differential equation. For example, if I talk about, let us say, algebraic equation y equal to minus 0.75 x to the power 4 plus 6 x cube minus 15 x square plus 12 x plus 2. I take differentiation of this with respect to x, we get first order ordinary differential equation dy by dx equal to minus 3 x cube plus 18 x square minus 30 x plus 12. So, now we can plot both the given function and its first derivative. You are representing one and the same function, but the representation is different. Wherever our function has local maxima or minima, that is where the slope becomes 0. So, we are able to spot these points. Also, we are able to spot that region of independent parameter space for which the function may be varying more rapidly or slowly. So, the rate equation is very important. You are looking at the same function from a slightly different perspective, but the real power is when we integrate this equation now dy by dx. Now, this 2 when we took differentiation was lost. So, when I integrate this, I will recover the first 4 terms and then there will be one constant term as shown here. So, now for different value of c, we can talk about the value of function y for varying values of x. So, c equal to 2 was the initial equation we started with, but now the beauty is if you have solved this first order differential equation not only for c equal to 2, now you get solution for all different values of constant parameter c. Okay. So, this is the beauty and power of differential equation. So, the first order differential equation that we saw, and when I integrate that, we are getting one constant of integration. Had it been second order derivative, we would have required 2 parameters. Third order equations, we need 3 parameters, so on and so forth. So, The order of differential equation tells how many additional conditions we need to solve it uniquely. So, I summarize what I just said here. General solutions of a linear ordinary differential equation of nth order is a family of functions depending on n independent arbitrary constants. So, the order tells us how many constants will be there in our solutions, and we have to ascertain whether we can provide those many conditions, then only we will be able to solve the given differential equation uniquely. What if we are given partial differential equation? Well, for partial differential equation, the general solution depends on arbitrary functions, not arbitrary constants like ODE. And so, arbitrary functions of independent parameters. So, this is very interesting. The problem suddenly becomes more challenging. The onus is on us to find this arbitrary function. These kind of situations we will encounter when we are using, for example, stress based formulation to solve problems of mechanics. So, in stress based formulation, first we get the stresses using constitutive law, we then find strains which are the gradients, the partial derivatives of continuously varying unknown displacement. So, we have to integrate all these strain terms to get displacements. Of course, there are compatibility conditions that we have to use, but in such a case when we do integration, we have to find arbitrary function for displacements. Some functions will appear. So, this becomes bit challenging. So, just to explain further what we just discussed, let us consider our continuous function depending on only one independent parameter space x. So, when I talk about del square u by del x square, so that is our ordinary second order derivative u double prime equal to 2. So, this would be second order linear non homogeneous ordinary differential equation ODE. If you integrate this, because this second order, we get now two constants of integration c and d. On the other hand, if u is function in x and y, and if now we are given the same fellow u x x equal to 2, this is second order linear non homogeneous partial differential equation, and its solution, instead of c and d, now I get arbitrary functions f y, g y, both continuously varying with respect to y. So, earlier we would have had tasks on our hand just to talk about c and d. Now, we have to evaluate and find f y and g y, then only we will be able to solve this given second order PDE. So, you can see our effort increases many folds. Other example, del square u by del x del y equal to 0, this is also second order linear homogeneous partial differential equation, and its solution would be two arbitrary functions, one function in x alone, other fellow function in y alone. So, these are arbitrary independent functions. Other important thing I would like to mention here, many a times we play with order of differentiation. Depending upon the methods available with us to solve a given order differential equation, we either expand the space or reduce the space. So, basically we play with order of differential equation. So, one example I give here, second order ordinary non homogeneous differential equation m x double dot plus c x dot plus k x equal to f. This is the equation we encounter in vibrations. So, it is the x is a continuous function with respect to independent parameter time. Our unknown function is x, only one unknown function. If I want to reduce order of this differential equation, I expand my parameter space. And how I do that? I introduce one more parameter. Let us say v, velocity equal to x dot. And when I substitute for x dot v in this equation, what do we get? mv dot plus cv plus kx equal to f. So, now I have two first order ordinary differential equations compared to single second order differential equation. So, you may say that what am I gaining here? Well, the advantage is we have reduced the order of given differential equation by expanding the space. Now, we have plethora of numerical methods which can be applied to first order differential equation, and those are robust methods, and we can solve this given differential equation very easily by splitting into multiple first order differential equations. Okay. So, this kind of exercise we do many times. Sometimes we combine several low ordered differential equation and get a single higher order differential equation. So, depending upon what is our purpose, which methods, which tools are available to us readily, we play with order of given differential equation. Okay. Let us talk about assignment on whatever we have discussed related to differential equation in assignment number 1. So, just to give you practice on proper classification of differential equations, this first question has been framed. So, there are 8 different types of differential equations and you need to correctly classify them. So, if I look at let us say 6 u x x x plus u x y y plus log u equal to 0. How would you describe this? This is first of all you look at the highest order derivative. So, that is 3. Third order, then you talk about whether it is linear, non-linear or quasi-linear. This is quasi-linear, homogeneous, partial differential equation. So, like that you classify all these equations. In question 2, please verify the expressions for u in terms of two independent parameter x and y, x square minus y square, e raised to x sin y. They are solutions of the partial differential equation. This is the Laplace equation, second order, linear, homogeneous, whether they satisfy the Laplace equation. And in the question 3, you are required to show that u as any function product of x and y independent parameters, where f is an arbitrary differentiable function, satisfies partial differential equation, the first order partial differential equation x u x minus y u y equal to 0. And after doing that, verify that all these functions product of which contain product of x y like sin x y, cosine x y, log x y, e raised to x y, x y cube etc. are solutions of the given differential equation. So, with this we will stop for this lecture. Thank you.